Welcome everyone. In this session, or now we'll talk about antenna theory. In this we'll talk about gain, propagation, etc. On completion of this session, you will be able to understand the concepts and you can explain principle of antennas, understand the antenna radiation, study antenna polarization, understand antenna gains, list and study types of antennas, understand what are the antennas we are using for mobile system, understand propagation pattern, then and list will mechanical features and different components of antennas you study. Antenna principles in a wireless system. Antenna is one of the most critical component. Okay. We know that the basic function of an antenna is to couple EM energy, electromagnetic energy, between free space and a guiding device. Another one is antenna radiation. This antenna radiation, in this antenna radiation, beam width is most important one. So here beam width between half power point in degrees are mentioned. How to calculate the beam width? That B is equal to 70 lambda by D, where B is beam width, D is the mouth of diameter of reflector, and lambda is wavelength. Now we can express wavelength in terms of beam width. So here if you can see that lambda is nothing but dB by 70. So I can put this value while finding out the gain of an antenna. So gain of an antenna is 6d by lambda the whole square, where AP is the power gain. Just now we discussed the lambda value, so I can put the lambda value over here, BD by 70. BD by 70. So we can find out that the gain is inversely proportional to the beam width. So beam width is more, gain is less, whereas gain is more, beam width is less. In these slides we are going to discuss about antenna polarization. Antenna polarization is nothing but orientation of antenna. Antenna polarization, normally we are using two types of polarization: vertical polarization and horizontal polarization. We know that RF waves are made up of EM fields, electromagnetic fields. So whenever the electrical field is parallel to the Earth's surface, it is known as horizontal polarization, and whenever electrical field is perpendicular to the Earth's surface, is known as vertical polarization. Normally we will find out that vertical polarization is most commonly used in wireless telephony. If a receive antenna is right angles to the TX antenna, so let's say TX antenna is having vertical polarization and receive antenna will have horizontal polarization. So these two antennas are called as cross polarized. In urban environment, energy gets scattered and depolarized during propagation. So polarization is not as crucial. Handset users hold the antennas at seemingly random angles. So handsets are using different random angles. Antenna gain. Antennas a passive device, so it does not produce power. It can only receive power and pass it on to another minus losses. An antenna can appear to have gain compared to another antenna or conditions. Gain can be expressed normally in dB or as a power ratio applies to both to radiating and receiving. We are using different types of antenna. In that normally we use directional antennas for mobile telephony. Directional antennas are having maximum radiations appear in one direction. Gain in one direction comes at the expense of less radiation in other direction. Antenna gain is relative, not absolute. So normally we always find out the gains with relation to the isotropic antennas. When describing antenna gain, the comparison condition must be stated or implied. Now we'll discuss different types of antennas. RF antenna converts high frequency radio RF signals on a cable into propagated waves, and this RF fields emitted called as beam or lobes. Different types of antenna, we use omnidirectional antenna, semi-directional antenna, highly directional antennas. Each category has several types, each having different RF characteristics and suited to fit a particular need. So first we'll talk about omnidirectional antennas. This omnidirectional antenna radiates energy equally in all directions around the antenna's vertical axis. So let's say this is vertical axis and it will radiate energy around the antenna's vertical axis. Simple to design, the dipole antenna is standard equipment in ODAs. Now we'll discuss applications of omnidirectional antenna. These type of antennas are used where coverage is required in all directions. Most effective when large coverage areas are needed around a central point. Commonly used for point to multi-point designs with a star topology. Another type of antenna is semi-directional antennas. These comes in different style and shapes. These are frequently used with wireless LANs, are patch antennas, panel antennas and Yagi antennas. Patch and panel antennas are flat and designed for wall mounting. On wall we mount this patch or panel antennas. Focus coverage of this antenna in horizontal arc of 180 degrees or less. So you can see that the patch antennas, if we are fixing it on a wall, it will cover 180 degree or less. Yagi antennas look like a long rod with tine sticking out of it, but they are usually encased in a plastic cylinder so the antenna itself cannot be seen. Yagi focus coverage in a beam with common vertical and horizontal beam width of 90 degrees or less. So normally you might have seen for TV antennas. So that are type of Yagi antennas. Beam width of 30 degrees or less are average type of antennas in this case. So we'll discuss directional patch antennas and usage of this directional patch antennas. Semi-directional antennas are usually used for short and medium range bridging. For example, there are two office buildings across the street. Need to share a network connection would be a good scenario in which to implement semi-directional antenna. So let's say I am in one building, I fix patch antenna, and there is another building across the street where I will fix another patch antenna and I can bridge the gap. I can cover the range. Third type is highly directional antennas. These antennas emit the most narrow signal beams and have the greatest gain. Already we discussed earlier, if the beam width is less, gain is high. So it will give greatest gain from antennas group. Common types of HDAs are parabolic, dish and grid antennas. Some models are referred to as parabolic dishes because they resemble satellite dishes. Grid antennas have perforated design. You might have seen the grid antennas like parabolic reflectors, plus they are having grid. Grid antennas have perforated designs for resistance to wind loading. So grid antenna good receptive of RF energy, and no RF energy would leak through the holes of grid. So you might think that there are holes are there, so energy may leak, but no, there is no leakage in the energy. Now these are highly directional antennas. Normally microwave antennas are highly directional antennas. We can observe that okay, this is our TX This is Rx. If I take a cross section, then this can be your Fresnel zone. First Fresnel zone, second Fresnel zone. This Fresnel zone concept is already covered. If it is not, we'll cover in the other session. HDAs are used for point-to-point communication links and can transmit at distance up to 58 kilometers. So normally 58 kilometer distance can be covered by using highly directional antennas. And uses of these antennas are to connect two buildings that are kilometers away from each other and have clear line of sight between them. Now we'll discuss some parameters of antenna, that is ERP and EIRP. First we'll talk about EIRP, that is equivalent isotropically radiated power. This is the power actually radiated by the antenna element. So this is important because it is regulated by the FCC. So how much amount of power radiated by antenna is EIRP. And effective radiated power. So we say that let's say X amount of power is transmitted or radiated by antenna, but are we going to get X amount of power? No, there are some losses. So antenna radiates all power minus losses is my ERP. Every direction gets some amount of power. Okay, so in ERP is the apparent power in particular direction equal to actual Tx power times antenna gain in that direction. So ERP is expressed in comparison to standard radiator. ERP is always compared with the dipole antennas, whereas EIRP is compared with the isotropic antenna. So let's say we talk about a comparison. Whenever we are talking about, let's say we are received so many percentage, X percentage, Y percentage, 70 percentage, 75 percentage, means what? We are referring percentage with 100. 100 is my reference value, reference point. Okay. So we were talking about reference antennas. In that we took example that normally we talk about 100%, 70%, 80%. So what do you mean by 80%? We are always referring 80 with something else. Similarly here we are using one reference antenna and we are comparing ERP with a dipole antenna. Okay. So isotropic antenna first we'll discuss. This is truly non-directional in 3 dimension, difficult to build or approximate physically, means difficult to build physically. Mathematically you can prove that, you can describe it, but while manufacturing or physically building it is very difficult. This is popular more than 1000 megahertz. This is popular. So that is for PCS, personal communication system, and microwave, etc. Dipole antennas. These are non-directional in 2-dimensional plane. Isotropic in 3 dimension. This is in 2-dimensional. Can be constructed easily, and this is popular. Less than 1000 megahertz to 800 megahertz. So for cellular, land mobile, TV, FM, this is commonly used. Now we'll talk about wave propagation. Wave propagation or antenna propagation, we already discussed this, that propagation of wave from the dipole is achieved by transformation from electromagnetic energy and vice versa. Resulting electromagnetic fields are right angles to the direction of propagation. So let's say electrical field is perpendicular and magnetic field is parallel to the earth surface. So it is vertical polarization. In most cases, propagation of an antenna can be described via horizontal or vertical radiation diagrams. We already discussed about this. In mobile communication, this is defined by magnetic field components, that is H plane, and electric field component E plane. Propagation characteristics is gain. We already discussed what do you mean by gain. Antenna without gain radiates energy in every direction, but with gain concentrates energy in defined angle of 3D space. Dipole is used as a reference for defining gain. So here at the last point you can see that we are always finding out the gain. As we discussed, isotropic antenna is very difficult to build. So how to calculate the gain of this isotropic antenna? So, but we know that dipole antenna is very easy to build. So we are referring dipole antenna DBD, that is dB of dipole plus 2.15 dB we are adding to get a gain with reference to the isotropic radiator, that is dBi. And impedance of okay, now we'll discuss about VSWR or return loss. We have talked about VSWR in our engineering, that is voltage standing wave ratio. Okay, and impedance of exactly 50 ohm can be achieved at one frequency. So VSWR defines how far the impedance differs from 50 ohm with wideband antenna. So VSWR is mostly because of the mismatch impedance. Power delivered from TX can no longer be radiated without loss. So there will be some kind of loss is always there. But if it is a reflected power is there, which is creating loss, is known as VSWR or will lead to VSWR. So power delivered from TX can no longer be radiated without loss. Part of power is reflected at the antenna and returned to TX. This is our return loss. VSWR of 1.5 is standard within mobile communication. So maximum value 50 ohms into 1.5 will give you 75 ohms, and the minimum value of impedance is 33 ohm. Now we'll talk about antenna's mechanical feature. Antenna mounted at exposed sites must withstand with required mechanical loading. This is where you are fixed or install antenna, it should be required mechanical loading. High wind velocity, it should withstand with the high wind velocity and vibrations. So BTS antennas are all normally exposed with high wind speed, so it should withstand with the high wind speed. Vibration, ice formation, because normally in very cold countries ice will form on antennas. Snow, corrosive environments, or extreme electrostatic loading via lightning. So BTS antennas should withstand with all these mechanical features. Now we'll talk about few components of antenna. Antenna system components. Antenna, here we'll have antenna, transmission lines, jumpers, directional couplers, duplexer, combiners, filters, and TRX units. So this will inform you about the antenna system. So we have antennas, transmission lines, these are jumper cables, directional couplers, duplexer we are using, combiners, filters, and then our TRX units. Antenna system, this is how the transmission lines will connect to trans and receive equipments. While installing, we should install in a such a way that the inner conductor and the outer conductor should be concentric. Otherwise, impedance will change. So don't bend this feeder cable or transmission lines large for direct connection with antennas. Use appropriate jumpers. Already we discussed in previous slide that transmission lines are connected to antenna with the help of jumper cables. Similarly, at the BTS end, transmission lines are connected to the BTS with the help of jumper cable. Secure jumpers against wind vibration, so that because of wind load it should not move here and there, and if it is moving here and there, characterization will lose, which will lead to VSWR. Then directional couplers. Directional couplers are a 4-port device, as we studied earlier in our engineering. It's a 4-port device, allows the desired portion of microwave power traveling in the main line to be coupled to secondary arm. So here you will find there are 4 different ports are there: input port, output port, and there are other 2 ports are there. So the coupled output from the directional coupler can be used to obtain the information. So the coupled outputs will couple the output, and we'll use that to receive information, to obtain information. These are available in coaxial lines, waveguides, and integrated circuits. So directional couplers are important components of antenna. Here we discuss that is, port number 1 is input port where the power is applied. Port number 3 is coupled port where a portion of power applied to port 1 appears. Some portion of power applied to port 1 will appear here. Port 2 is transmitted port where the power from port number 1 is outputted, less the portion that went to port 3. So port 1 is transmission of power minus some part of power is moved via port number 3, and this will appear at port number 2. Directional couplers are frequently symmetrical, so there are also port number 4, which is isolated port. So if we normally you can observe the second diagram. This is input minus coupled port, that is port number 3, and output you will receive at port number 2. However, a device is not normally used in this mode, and port 4 is usually terminated. So this is what we discussed. Port 4 is terminated with 50 ohm load. Another components of antennas are isolators and circulators. RF isolator, this is a 2-port ferromagnetic passive device. This is used to protect other RF component from excessive signal reflection. If the excessive signal reflections are there, it will save, or it will protect RF component from excessive signal reflection. Ideally 100% transmission in forward direction and 0% in the reverse direction. Another device is RF circulator. This is 3-port ferromagnetic passive device used to control the direction of signal flow. So here you will find circular flow of signal in one direction. This circular flow of signal used to separate the transmitted signal from the received signal present at antenna. Once again we will repeat that circular flow of a signal in one direction used to separate transmitted signal from received signal present at an antenna. Use as both TX and RX. Then duplexer. This is also a 4-port passive device used to separate transmit and receive signals. So how will I separate TX frequency and RX frequency? This is 4-port device which will separate TX and RX signals in single antenna. Duplexer will allow simultaneous transmitting and receiving on one antenna. Examples are given. Not till 1900 MHz BTS includes internal duplexers are there, whereas not till 800 MHz BTS does not include duplexer, but commercial units can be used if desired. Duplexer is composed of individual bandpass filters to isolate TX from receive or RX frequencies, receive frequencies, while allowing both to access antenna. So here we discuss principle of antennas, how antenna works, understand antenna radiation, that is your vertical and horizontal radiation, study antenna polarization, what do you mean by antenna polarization we discussed, understand antenna gain, list and study antenna types, that is omnidirectional, semi-directional, highly directional antennas, understand antennas for mobile system, different types of antennas we use for mobile system, understand propagation pattern, mechanical features, and different components of an antenna. Okay, thank you very much.